Okay, great. All right, good afternoon, everybody. My name is Bob Sinkovits. I am the Director of Education here at the San Diego Supercomputer Center. I'm also a physicist and a computational scientist. I've been doing this for quite some time. And this presentation today is going to be a little bit different than some of the other ones we've seen. It's really targeted at folks who are what we're calling non-programmers, even though we think everybody could benefit. And we're just going to be going over some of the general principles of parallel computing that we think everybody should know. I have a link here in my presentation to GitHub repo that contains a few Jupyter notebooks that I use to generate some of the figures for this presentation. All right. Well, let me just minimize that. All right, so this is an encore presentation that I gave. I think it was just yesterday to a larger audience. So this session, on parallel computing concepts, it's really targeted. I could sum this up with it's targeted at everybody who is ever going to be touching a parallel computer. So if you currently run, or you plan to run, or you're thinking about running applications on parallel computers, I think you'll get a lot out of this. I know that we have mostly students on this call, but for those of you who are writing proposals for computer time, this would apply to the PIs, and some of you will be pulled in as co-PIs to help with the writing. I think this will all be valuable. If you purchase time on compute resources, and you want to maximize return on your investment, and here we're talking primarily about cloud computing resources. So when you go to Amazon or Google or Microsoft Azure, you're paying real money to get that compute time, and you want to make sure that you're getting the most out of it. If you're in a position where you or your lab is considering purchasing hardware, I think you'll find this valuable. And finally, this is directed at everybody who is simply curious about parallel computing. So a little bit of background on why we are doing this training. So first of all, much of the training in parallel computing is targeted at people who write their own parallel applications. And this training really looks at programmer topics, which we're going to be seeing in the second set of lectures in this series. So things like MPI, Openmp, CUDA, profiling, performance tuning. So these are all really valuable topics, but again, only if you are actually developing code. So as a consequence, everybody out there who's an end user, who's not developing their own applications, rarely or never gets a proper introduction to parallel computing. So again, if you're a developer, you're a computer scientist, you probably see this. Otherwise, you never really get a good grounding in parallel computing. So even if you don't write code, it's really important that you understand some of the basic principles of parallel computing so that you can make the most effective use of the valuable advanced cyber infrastructure, whether that's machines like Expanse or other resources that are allocated through the Exceed program, cloud resources, or even your own lab's resources. So I want to talk a little bit about some of the myths of parallel computing, and hopefully that nobody believes all three of these myths, but I think it's still worth going over. Well, one of the myths, and this one doesn't seem to be as widely believed as it had been in the past, but that's that parallel computing is for astrophysicists, engineers, climate modelers, and others who are working in traditionally math-intensive fields. So I'm sure there are some of you on this call who fit that description, but I bet that a lot of you also come from social sciences, life sciences, biomedical sciences, arts and humanities. So while this myth may have been somewhat true decades ago, there was a time, say in the 80s and the 90s, when our user base was much narrower. It really has expanded to include just about everybody now. And I always like to share a story. I was doing a tour of our data center about 5-6 years ago. thank you, about 5 or 6 years ago. And one of the people on the tour was from one of the social science departments here at UCSD. And this faculty member said, wow, this is amazing. Look at all this hardware. I wish I could use this. I wish it was accessible to me. And I explained to him, I said, these resources, they are there for everybody who has a problem that requires parallel computing. So again, don't be scared away if you're not one of our usual suspects in physics, chemistry, engineering. So another myth, and I think a lot of you probably have some of the background to know this, but that one of the myths is that throwing more hardware at a problem is automatically going to reduce the time to solution. So first of all, parallel computing is only going to help if you have an application that's already been written to take advantage of parallel hardware. And then even if you do have a parallel code, there's going to be an inherent limit on scalability. So this is something that we see come up quite often, where somebody will be running an application on the supercomputer, but they're using so many cores or so many nodes that they're way out there in the past the point where they're really getting diminishing returns. So if you can solve your problem in half the time on 2 nodes relative to 1 node, that's great. But if you keep throwing more and more hardware at it, eventually you're going to get a point where the performance gains really peter out. And I should say though that there's one caveat here. I'm not really going to talk about it today, but there's a type of computing called high throughput computing. This is where we use parallel computing to run many instances of a single core job. And when we do that, we do get pretty much perfect scaling. And then the third myth is that you need to be a programmer or software developer to make use of parallel computing. And this is one that again was true maybe 25 to 30 years ago. Parallel computing was relatively new. There weren't that many people who were doing parallel computing. And there really wasn't a very rich ecosystem of software. So if you were a computational chemist or a molecular biologist, you pretty much had to write your own. But now there are lots of great third-party applications in many fields. So you really don't need to be a programmer or software developer anymore to make use of parallel computing. So, in a nutshell, most of you are going to be using somebody else's code. So if you're doing, say, weather or climate modeling, you might use WRF, which I'm showing here on the left side of the screen. Other codes include CESM and MPass. If you're doing molecular dynamics, biological systems, you might be using software like Amber or GROMACS or NAMD. If you're doing electronic structure calculations or computational chemistry, you're probably going to use CP2K or Gaussian or GAMES or Quantum Espresso or MALPRO. And then if you're interested in phylogenetics, constructing phylogenetic trees from genomic data, you're going to use software like RaxML or Beast. So I don't want to encourage anybody from developing software. There are many problems for which we do not currently have robust third-party apps. But look around first, see if somebody else has done it. And like I said, for many of these communities, there's already a whole host of software out there that does what you need to do. Parallel computers, going to talk about it just very briefly here. And then at the end of this presentation, we're going to do about a 10 to 15 minute overview of Expanse. So parallel computers, these modern clusters, they consist of multiple compute nodes connected together by a fast network. So these compute nodes, essentially, they're the same as servers or even very powerful desktop systems. They've got the same kinds of memory, same kind of processors in there. It might be a higher grade, what we call enterprise grade hardware, which is meant to be run 24/7 for years on end. Might be faster clock speeds or more memory, but generally it's going to look like the computing that you're already familiar with. What makes this thing a parallel computer is the network, and a lot of money goes into the fast interconnect so that these compute nodes can communicate with each other. Typically, the nodes are going to contain one or more, generally two multi-core processors. And as I mentioned earlier, to effectively use this software, we need applications that have been parallelized so that they can be run on multiple cores within a node or across multiple compute nodes. So what I'm showing here on the right, and again, since we're going to be talking about Expanse at the end here, I'm not going to go into the details, but this is a logical view of a supercomputer, showing the types of compute nodes, networking, and storage that we have. Okay, with that, now that we got through the background, we're going to talk about a few parallel computing concepts. And this is sometimes one of the hardest ones to really wrap your head around, and that's processes and threads. So both of these are independent sequences of execution. They're both ways that you can implement parallelism in your code, but they operate somewhat differently. So to me, I think of a process, that the best description of it is an instance of a program. So you're running a program, has access to its own memory, to its own state, so it knows where you are in the execution, the values that are assigned to variables, and file descriptors. So a process can open and close files. Now, a thread is a lightweight entity that executes inside of a process. So every process is going to have at least one thread, and then the threads within a process, though, can access the shared memory. So again, each process will have access to its own pool of memory, but multiple threads within the process can share memory. Right. So if you look online for descriptions of the difference between process and thread, a lot of these tend to be geared toward computer scientists. They get awfully nerdy very quickly. But I did find two resources, and I think if you really, really want to understand processes and threads, if you want to go a little bit deeper when we're done with this session, there's one discussion here on Stack Overflow, which again, I think it's a little more CS developer oriented, but I think you'll be able to follow it. And then there's a much more informal description at that second URL. Right. Moving on, some of the key differences between processes and threads are summarized here. So a process is going to incur more overhead. Processes are what we call heavier weight, but they're also more flexible. So multiple processes can be run within a compute node, or they can be run across multiple compute nodes, what we call distributed memory parallelism. Now threads, these are lighter weight. If you're going to be doing programming, often they're easier to implement. They incur less overhead, so it doesn't require as much computational effort to create and destroy threads or manage them. Threaded codes can use less memory, since the threads within a process have access to that same pool of the data and all of the data structures. Now, the drawback with the threads, though, is that they're less flexible, so multiple threads associated with the process can only be run within a compute node. So when you hear processes, you got a lot of flexibility. You can run it on a core. You can have processes running on multiple nodes. Threads, everything has to be within a process, within a compute node. So why do we care about processes and threads, especially if you're an end user of supercomputers and you're not going to be developing your own code? So distributed memory applications, so multiple processes or instances of the program, again, these can be run on one or more nodes. So if you want to get the maximum scalability, you're going to have to go to processes. Shared memory applications, the mention should be run on a single node. You're not going to get any performance benefits by going across multiple nodes. We also have something called hybrid applications, and these can be run on one or more nodes, but you need to consider the balance between threads and processes. So for a lot of the software that's been developed to run in these hybrid modes, you need to think about what your balance is going to be between processes and threads. And you may also need to consider how processes and threads are mapped and bound to cores. So we're not going to get into these details today of how you actually do that. We have, I believe, next week's session and the week after that are going to be focusing on actually running jobs on the supercomputer. Again, we're just looking at the a high-level overview of parallel computing. So also, if you're aware of threads and processes, this is going to help you to understand how your code is utilizing the hardware and identify common problems. For example, if you set up your job incorrectly, you may find that multiple processes are all trying to run on the same core, or multiple threads are using the same core. You may also find sometimes that processes are left over from another job. And understand the distinction between the two is going to make it a little bit easier to diagnose any issues you have. All right, so I said that this is not a not a programmer talk. I'm not going to be teaching you MPI or Openmp today. These are things, though, that I think everybody needs to be aware of. So MPI is message passing interface. So message passing means that we have multiple processes, and they're explicitly sending messages between them. So when they need to share data, when they need to exchange data, they will make a call to a function in the MPI library to pass that data. So MPI is a standard for parallelizing C and C++ and Fortran code to run on distributed memory, multiple compute node systems. I should mention, though, that you can also use it within a compute node. So although it's not officially adopted by any of the major standards bodies, it's really the de facto standard for distributed memory parallel computing. And by de facto, we mean essentially almost everybody uses it. Now, one thing that gets a little confusing is the distinction between MPI, the standard, and the implementations. So in fact, this came up when I responded to a question yesterday when I gave this presentation. So MPI is the standard, but there are multiple open source implementations. So there's OpenMPI, MVAPIC, MPIC, and there are also vendor supported versions of MPI, such as Intel MPI. Generally, you probably don't need to worry about the differences in implementations. They all adhere to the MPI standard. They all use the same API. So a code that's been parallelized using MPI can use any of these. Typically, these are things that if you're really trying to squeak out the absolute best performance of your application, you might want to get in and tinker with things that are not part of the API, such as buffer sizes for the communication. But that's getting into really deep level of detail. Generally, you just program to the MPI standard and don't worry about the implementations. So I mentioned this earlier, that MPI applications, they can be run within a single node, within a shared memory node. And all widely used MPI implementations, they are optimized to take advantage of the fact that you can communicate data between processes faster within a node or intranode than between nodes. MPI is portable and you can use it anywhere. This is one of the reasons that MPI is so powerful. Many years ago, when I first started doing parallel computing, MPI was kind of on the horizon. There were a lot of other options out there. Some of them were vendor specific. So if you parallelize your code, you might be tied to a particular resource. MPI solves the portability problem. And then finally, MPI is often synonymous with distributed memory parallelization, but there are other options out there that are gaining adoption. One you might come across is Charm++. The biggest use case for Charm++ right now is the NAMD, molecular dynamics software. Very highly scalable MD application. Our former director at SDSC, Mike Norman, who's a computational astrophysicist, is rewriting his major applications using Charm++. There's also things called UPC, Universal Parallel C, I believe it is, developed at the National Labs and X10. So most often you're going to be seeing MPI, but you may come across other ways of doing distributed memory parallelization. Now, again, I said this is not a programming session. There are going to be lectures in part 2 of this series that actually get into MPI, OpenMP, and other programming topics. If you have no interest in programming whatsoever, you can ignore what's going on the left-hand side of the screen. But I'm just showing here the first program that many of you may have written. It's simply hello world. This is a C implementation. An MPI version of that is a little bit uglier. Once you learn MPI, you realize that this isn't as intimidating as it looks, but it's still pretty low level. We're making calls to the MPI library to explicitly communicate data, synchronize processes, and so on. So if you're not a programmer or an application developer, you do not need to know MPI, but you do need to know that it exists. And sometimes you may need to build your own executable. So you're taking somebody else's source and you need to compile it for to run on a parallel computer. In that case, you need to be aware that it's an MPI application and you'll need to use the appropriate wrappers. So these would be typically compiler names pre-appended with MPI. So MPI CC is a wrapper that would compile a C program that would link in the MPI libraries. Okay, so if we're going to be doing thread level parallelism, the most common way to do this is OpenMP. So this is an API for shared memory, again, within a node, parallel programs. And we have OpenMP bindings for C, C++, and Fortran. So OpenMP gives you a collection of compiler directives, library routines, and environment variables. We're not going to be using the library routines in the same way as we are in MPI. So they're more to gather information, say on the number of threads that are executing, or the number of cores that are available for your process. Generally, we're going to be using primarily the compiler directives. OpenMP is supported by all major compilers, including IBM, Intel, GCC, which is the GNU compiler collection, PGI, and the AMD optimizing C and C++ compilers, or AOCC. So on Expanse, we have the Intel, PGI, and the AOCC compilers. Like MPI, OpenMP is portable and you can use it anywhere. When I said OpenMP is supported by all major compilers, I have never seen a modern compiler that does not support OpenMP. So regardless what system you go to, if you're running on Expanse, if you're running on an IBM supercomputer somewhere, other Expanse Xseed resources, you're always going to have OpenMP available. So although OpenMP is often synonymous with shared memory parallelization, just like MPI, there are other options. So there's a programming language called Silk, which looks an awful lot like C, which has and extends the syntax a little bit. Something called POSIX threads or P threads. And then there are also specialized libraries for Python and R and other programming languages. And just to show a programming example, again, if you're not a programmer, you could just ignore the left-hand side of the screen. If you have a little bit of programming background, you might be able to read this code. Essentially, what we're doing is allocating 3 arrays, A, B, and C. Each are going to have n elements. We're going to do some initialization. We're just going to assign that values to A and B. And then we're going to add them element by element and store them in a new array C. So showing here what a parallel version of this code would look like. So we've added a few directives. Main thing is that we added this pragma down near the bottom, which is going to parallelize that loop. It's going to take iterations of that loop and it's going to spread them out across multiple threads. OpenMP code, or code that's been parallelized using OpenMP, could still be a little dense, but it tends to be much more readable since the changes are often minor relative to the original code. Just like MPI, if you are not a programmer or an application developer, you do not need to know OpenMP. You just need to be aware that it exists. And if you are building your executable, if you're taking against somebody else's source code and creating an executable, you'll just need to know to use the appropriate compiler flags. Unfortunately, these are not standardized. So I forget which of these apply to which compiler and Expanse, but across the Intel, PGI, and GCC compilers, they use different flags, -F Openmp, -Q Openmp, or just -MP. Now you'll notice here, if you're a C programmer, that this pragma, it begins with a hash. So what this means is if you're not enabling Openmp, that's just going to be treated as a comment. Okay, so kind of taking a look at the big picture, for Openmp and Mpi. So on the left-hand side, we're going to use Mpi to manage multiple processes, and then things like Mpitch and Mvapitch and Openmpi. These are all implementations of Mpi. So they all adhere to the Mpi standard. They implement the API. On the right, we talk about threads. So multiple threads can be managed using Openmp, and then Openmp is actually implemented by the compilers. Again, it could be GCC, Intel, PGI, AOCC, or others. All right, so I mentioned this earlier, that we can also have hybrid applications. And we're seeing that a lot of modern parallel applications are built using a hybrid approach to take advantage of both distributed and shared memory. And you can see why you might want to do this. So first of all, if you have a purely threaded application, say parallelized using only Openmp, you're going to be restricted to how far you can scale. You're only going to be able to run within a compute node. But for straight MPI applications, there are limitations also. So distributed memory apps, they may have higher memory requirements. And I'll show an example of how the memory usage can grow a little bit for when parallelizing with MPI. And they also have more overhead when running within a node. So you might be able to reduce your memory footprint and reduce your runtime a little bit by using multiple threads within a process. Okay, quick question here from Maria. Could you comment on the difference among processor, process, and rank? Sometimes those terms are used interchangeably. Yeah, they are, but they shouldn't be used interchangeably. So I'm going to say, strictly speaking, a processor is a piece of hardware. And the terminology gets a little confusing. Sometimes a processor refers to that entire chip that plugs into your motherboard. Other times a processor is used to refer to one of those compute cores within the chip. So on Expanse, we have 2 of these 64-core chips, each with 64 CPUs. Now, a process is, I gave a definition for it earlier, but I could reiterate it here. You could think of a process as an instance of a program. A process is something that's running on the hardware. It has its own pool of memory, its own program counter, and it can manage files, open and close files. And then rank is a way to distinguish between processors in a parallel job. So let's see if I could go back here to the MPI example. I'm not sure if you could see my cursor, but there's a line here, MPI com rank. What that call is doing is, let's say that we're running this on, we're running 16 processes. Each of them is going to get an ID. So it would be rank 0, rank 1 through rank 15. So that's just a way to distinguish between multiple processes. So Maria, did that answer your question? Great, good, excellent. Okay, so moving on. So for the next few slides, we're going to talk a little bit about hybrid applications And rather than using something so big and complicated like Expanse or any other real supercomputer, we're going to imagine a very, very simplified parallel computer. So it consists of just 2 compute nodes, and each of those nodes is going to have 16 cores. So of course, this is unrealistically small. Most supercomputers are going to have hundreds to thousands of nodes. The number of cores on new systems is probably going to be 64 or greater. And we're going to assume that these 2 nodes could communicate with each other through an interconnect. So this on a supercomputer is going to be typically InfiniBand, which is a very, very high speed, low latency network, or it could be 40 gig or 100 gigabit Ethernet. So using this, this simplified system, we're going to look at different ways of running hybrid applications. So we're going to start with message passing applications, something that's been parallelized, say, using just MPI. So applications been parallelized using message passing are typically executed with 1 process per core. So this example shows an application where we're running 32 processes across the 16-core node. Now, occasionally, those processes are going to have to communicate with each other. The MPI implementation is going to handle both the communication between processes on a node and processes that belong to different nodes. So under the hood, they'll be using different protocols. But to the programmer, it looks all the same, so you don't need to distinguish. Now, if we have a threaded application, say parallelized using just Openmp, we're going to be restricted to running within a single node. So here I'm showing a case where a threaded application is running 16 threads on 16 cores. Now, those of you who come from a computer science background, you may realize that this isn't strictly absolutely true. You can, technically any programming model can be mapped to any hardware, but in practice, if you try to run a threaded application across multiple nodes, you're going to get terrible performance. 2 supercomputers ago, so before Expanse, we had Comet, and before Comet, we had Gordon. On Gordon, we had installed a, I'm going to call it a somewhat experimental software that would aggregate multiple compute nodes and make it look like a large shared memory node. So kind of under the hood, it would handle the communications, but it was, except for a certain class of applications, it really didn't have great performance because every time threads needed to synchronize, you were communicating over the network. And now I'm not really aware of anybody who's trying to make that approach anymore. All right, now hybrid applications, this could be done multiple ways, but typically it's going to be MPI plus Openmp. So any combination of threads and processes within a node is allowed. Excuse me. So here we see an example showing 2 processes per node and 8 threads per process. So I use those orange rectangles to indicate a process encompassing 8 nodes, and then we have a thread running on each node. Now, a typical scenario is to run 1 process per node and then use threads within a node. But I'm going to say, though, that this is becoming a little less common as the number of cores on a node continues to grow. So if we go back to Gordon and then to Comet, previous 2 supercomputers, I believe that Gordon had a total of 16 compute cores per node, and Comet had 24. On Expanse, we have 128 cores, and sometimes you find that a threaded application just doesn't scale well enough onto that many cores. So we're going to see more and more cases where you need to decide your balance between cores and threads, and this gets a little tough. You know, we have, if we're running one of these hybrid applications, we have a whole spectrum from running 1 process per node, and then however many cores we have, that number of threads, all the way down to 1 process per core and everything in between. So the In order to decide this, you're really going to have to, for your application, and it's going to vary from app to app, you're going to have to do benchmarking to determine what the runtime is and what potentially what the memory usage is for those different combinations of threads and processes. And you're definitely going to find some applications out there that even now can take advantage, can run 128 threads within a process and get good scaling. But you're going to have a lot of other ones that are going to fall somewhere in between. All right, so we're going to switch gears a little bit. We're going to talk about Amdahl's law and limits on the scalability of parallel applications. So if you know one law in parallel computing, Amdahl's law is the one to know. I would say this is the E equals MC squared, or the F equals MA of parallel computing. It's a really, really simple law, but it's so deep and so profound. So it describes the absolute limit on the speed up of a code as a function of the proportion of the code that can be parallelized and the number of processes that are used. So truly the most fundamental law of parallel computing. So let's say that P is the fraction of the code that can be parallelized, and S is the fraction of the code that must be run sequentially. And of course, S plus P are going to equal 1. And when we say the fraction of the code, we don't mean fraction in terms of number of lines of code or number of subroutines. We mean where the code is spending its runtime. So we look at those operations and we decide, can that be parallelized or must be done serially? So a good example of a typically serial operation might be reading in the data set at the start of a job. For some applications, especially climate and weather that need to operate on very, very large grids, often that can be parallelized. We can do parallel I/O, but in general, there's going to be a lot of I/O that needs to be done serially. Parallel operations is when we identify tasks that could all be done independently. So let's say we're given the task of, say for this group, you're given 1,000 numbers and we need to calculate the sum of it. So we could divide that into, let's say round up and say there are 100 of us here. We can divide that up into 100 chunks, and each of you can be working on your part of the problem, on your set of 10 numbers. So that's something that can be parallelized. Now, after that, we're going to have more and more limited parallelization. Eventually, we need to have somebody who will go around, collect all of the sub-results. So you can see that there can be mixes of parallel and serial content. And N is going to be the number of processors that we use. So Amdahl's law says that the speed up as a function of the number of processors is 1 over 1 minus P plus P over N. And when you look at this, it's kind of intuitive. So that P over N term, that says, okay, that's the parallel content. And I'm going to, that portion of the code is going to speed up proportionally to the number of processors that I use. So if I use 2 processors, that part will take half as long, 4 processors, quarter as long, and so on. The other term in the denominator, that 1 minus P, that's the serial content. And that's going to be fixed no matter how many processors we throw at the problem. That's not going anywhere. So as we let the number of processors go to infinity, which of course you're never going to do, but in theory, the speed up, the maximum speed up is going to depend only on the proportion of parallel content. So in the limit n goes to infinity, we get 1 over 1 minus P over, or that equals 1 over S. So you look at this and you say, that doesn't look too bad. But as we show in the next slide, it doesn't take much serial content in order to quickly impact the speed up. So this is one of the figures that that was generated using the GitHub repo. And I'll post that again in the chat when I'm done with this session. So here we're looking at the speed up of a code. How many times faster does the code run as a function of the number of cores? And we're looking at this for codes that have, 50%, 75%, 90, and 95% parallel content. And we can see, even if we have 95% parallel content, no matter how much hardware we throw at the problem, we're only going to get a maximum speed up of 20. Now, if we go one step further, let's consider code with 99% parallel content. And you're thinking, wow, that's pretty good. I was able to parallelize 99% of the code. Even with that 1% serial content, your maximum speed up is going to be limited to 100x. Oh, and question here from Alexander. Yes, cores and processes are synonymous, and I should have been a little bit clearer about that. You know, when I was answering Maria's question, I did address that there's a little bit of an ambiguity. So by processor, we sometimes mean that entire chip, but in this context, I'm using processor to mean one of those cores or one of those CPUs. Yeah, so in this case, cores and processors are synonymous. All right, so we getting back here, we look at our code, 99% parallel content. You're thinking, wow, that's great. And you're still only going to get a maximum speed up of 100, assuming that you had thousands of processes to throw at this problem. On top of it, if you look at this arrow, the arrow in the center of this plot, that is pointing to the data point corresponding to 128 cores, which is the number of cores that we have on an Expanse compute node. And you can see that we are only getting a 60x speed up. So we're really making pretty terrible use of that 128 core node, even neglecting what the max speed up is. Just the kind of speed up that we get at realistic core counts, we're already doing pretty bad. I'm going to say that this application should probably be run down on somewhere more like 16 cores, if even that. All right, so there are other limits on scalability beyond Amdahl's law. Amdahl's law is going to set a theoretical upper limit on the speed up. But there are other factors that affect scalability. So there's communications overhead. There's the problem size, limitations due to problem size. So let's say I'm doing a molecular dynamics calculation that has 1 million particles. Okay, you say, okay, we could divide that across two processes, give each of them 500,000 particles, and we can continue dividing, but we can only go so far. If we get to the point, I mean, obviously we can't go beyond past the point of having 1 particle per processor, but even long before there, we're going to have so little work assigned to each of those CPUs that we're not going to be scaling. And there's also an issue of uneven load balancing. So in these real life applications, when you consider communication overhead and synchronization, this is when, say, all the threads or processes must complete their work before proceeding, or problems with irregular geometries instead of nice Cartesian grids. You know, weird shaped geometries, things that we see in the real world, that's going to really impact the scalability of your code, and your speed up is going to be much less than predicted by Amdahl's law. So load balancing. This is an issue where when we parallelize a code, we need to take all the computational work and we divide it up into chunks that it can be executed independently. So if the work cannot be distributed evenly, then processes will sit idle waiting for the longest chunk to finish. So let's say that we have 4 tasks. These could be processes or threads. Could have parallelized this using Mpi or Openmp, but assume that each of these tasks or CPUs is assigned a different chunk of work. So we start in the beginning, we give task 2 a big chunk of work, and then task 0, 1, and 3 smaller chunks. So what's going to happen is task 1 is going to finish, task 1, then task 3, then task 0. They're going to be sitting there. They're going to be idle, just waiting for task 2 to finish. So that is going to impact your performance and your scalability. So now when we get to that first synchronization point, now we hand out new chunks of work. In this case, task 1 was assigned the longest one. So now, task 2 finishes early. it's wasting a lot of time waiting for everybody else to catch up, followed by task 0 and task 3. So this can really cut into the performance and the scalability. And then finally, there's communications overhead. So if you're working in a field like computational fluid dynamics, magnetohydrodynamics, climate, weather simulation, these generally involve solving systems of partial differential equations, and we do this by discretizing it and solving it on a grid. And then if we're doing this in parallel, we would take that grid and we would distribute it across processes in order to achieve parallelization. So again, this is a unrealistically small example. If you were really doing climate or weather simulation, you would be looking at tens of thousands to potentially millions of cells. But here we're just looking at a very simple problem in 2D. So we have this 16 by 16 grid that we're going to divide into 4 8 by 8 chunks. And we're going to distribute these across the processes. So let's say we have process 0, 1, 2, and 3. Now, normally when we solve these systems of PDEs, it involves a pattern communication where each cell is going to be updated using the values of the 4 neighboring cells. So I've highlighted one in each of those 4 domains. So each cell in red, when we want to update the value, it's going to need the values from the 4 cells, essentially up, down, left, and right. And for cells that are within the interior of a chunk, you can see that we don't need to do any communications. Each of these processes can execute independently. Where we're going to run into problems, though, is for those cells that are at the boundaries. So if it's a cell that was at the boundary of one of those domains, it's going to need data from a neighboring process. And then to accommodate this, we need to create a halo of what we call ghost cells, which can be used to store data that is collected from the other processes. So this data movement, it's going to depend, how quickly we do it. It's going to depend on both the latency and the bandwidth of the network, and it introduces communications overhead. So, for example, if we look at those top 2 processes, the one in the upper left is going to pass that column that I now highlighted in dark blue over to the process to its right. And that's going to be stored in one of those in that column of ghost cells. And then the process on the top right, the column that I highlighted in dark green, that's going to have to be communicated to the process in the upper left. And then we need to do this across all the processes. So fortunately, we can do this in parallel. We don't need to do one set of communications and another. But still, this does incur overhead. You're going to find that the time to communicate that data is based on both the latency, how long it takes to move that first byte of data, and the bandwidth, the rate at which you can move data. So by now, you're probably getting a little depressed about parallel computing, thinking, there's Amdahl's law and these other factors that affect scalability. How does anyone ever use all the cores on a modern on a single modern compute node, let alone the full power of a large supercomputer? So I will say all is not lost. The reality is, first of all, that most parallel applications do not scale to thousands or even hundreds of cores. If you've logged into Expanse already, and you look at what's running in the queue, you'll see that there are lots and lots of small jobs in there, often using less than a full node. They might only be using 1 or 2 or 4 or 16 or 32 cores within that node, and then sharing that node with other applications. So again, the reality is a lot of applications just aren't going to scale that far. Now, the ones that do achieve high scalability, they employ several strategies. So first, they don't try to solve a fixed size problem on an increasing number of cores. Instead, they will try to solve larger problems. So essentially, they're growing the problem size with the supercomputer. And this kind of scaling, it's described by something called Gustafson's law. Don't really have time to get into it here, but you could think of it as the law that governs weak scaling, looking at how the runtime scales as we increase the problem size proportionally with the number of CPUs or compute nodes. We can also overlap the communications with computation. So going back a slide, while we're moving data between these processes, we could be doing the computation on these interior cells so that by the time we get to the cells that are along the boundary, we already have that data there. So that's a really important strategy. We could use dynamic load balancing to assign work to cores as they become idle. And then we can also increase the ratio of computation to communications. So if you're doing more computing within each cell between these communications events, your code is generally going to scale better. So a good example is comparing standard computational fluid dynamics with what we call reactive flow or combustion, where in addition to the fluid flow, we also need to solve the chemistry that's going on within each cell. So that chemistry is really expensive. That's going to add to the computational loads. Now you're going to be doing more computing relative to the communications. All right, so we're getting pretty close to the end here. We're going to talk about running parallel applications. So we've covered the basics parallel computing, stuff that I think you all need to know, hardware and threads and processes and hybrid applications and implementing parallelization, Amdahl's law and scalability. Oh, so let me answer a question first from Anmol Kapoor. So if a core becomes idle, it can, so to speak, request the next process to complete. Yes, that is exactly what goes on in dynamic load balancing. So I'll see if I could offline show you an example in Openmp where instead of taking the iterations of a loop and dividing them up evenly at the beginning, instead we can use a dynamic assignment so that essentially we hand out a chunk of work to each of the threads. And then once the thread becomes idle, essentially the thread is raising its hand and saying, okay, I'm ready for more work. And then it's assigned a chunk. So yep, that's exactly how the dynamic load balancing would work. All right, so getting back to running parallel applications, all this theory and background are great. You really need to know this, even if you are, say, a PI who doesn't touch hardware computers anymore, but you need to write that allocation proposal. You need to know all this stuff. But how do we know how many processes to use when we're running our application? So the only way to definitively answer this question is perform what we call a scaling study, where a representative problem is run on different numbers of processes. And a representative problem is one that has the same size, say the grid dimensions or number of particles and number of images and number of genomes, and the same complexity. Let's say we're doing computational chemistry. Is it DFT? Is it CCSD? Each of these have various levels of complexity and runtime, the type of analysis we're doing, the physics that we're including in the simulation. So your representative problem, it doesn't necessarily need to be run as long as you would do your full simulation, but it has to look like a problem that you're trying to solve. Otherwise, the benchmarking and scaling study is going to be useless. So I'm going to talk a little bit about how you can present your scaling results. And this is but both for yourself, so you get your own insight into how the code is behaving, but also if you're making a request for compute time. So the plots on the left and the right, they show scaling curves for two different applications. So looking at these, it's pretty hard to tell which one is better, especially at the large core counts, that the runtimes are indistinguishable. So we plotted this on linear axes, and then when we get down to the right two dots on each plot, for the 64 and the 128 cores, I really can't tell which one is doing better. But if I plot this on log axes, I'm going to get a lot more insight. So a code that has perfect scaling is going to, the runtime as a function of cores, it's going to look like a straight line on a log plot. You can also add a solid black line to indicate what the linear scaling should be. And I think it also helps to plot the parallel efficiency on the right-hand axis. So the parallel efficiency is the speed up divided by the number of cores. So for example, if you run on 128 cores and it's 128 times faster, that would be a perfect parallel efficiency. So we can see here the code on the left. Generally, you're not going to see this. This is an application that has absolute perfect scalability. Every time I double the number of cores, the runtime is cut in half. And you can see right across the top, that blue line, that parallel efficiency stays at 1. The plot on the right is what you're going to see more often. As you start running more and more cores, of course, the code is going to execute more quickly. Let me take that back. It's not always going to execute more quickly. Eventually, if you run too many cores, you may find that the runtime eventually increases rather than decreasing. But again, in this case, we're seeing that as we add more cores, we keep running faster, but we're running at worse and worse parallel efficiency. So the question is, where should you be running? Where on this scaling curve should I be? So this is a really important question. It depends a lot on your computational needs, how time sensitive the calculations are, and I guess also whose hardware you're using. So if your work is not particularly sensitive to the time to complete a single run, I'm going to say consider using a core count where you're at or very close to 100%, maybe 90% or better, even if that means sometimes that you're only running on a single core. If you have a high throughput workload, you're doing a parameter sweep, the same kind of calculation run many times with different sets of input. You really don't care how long it takes any particular run to finish, but what matters is how long it takes to get through that whole suite of runs. Yeah, run that at small core counts where you're getting near perfect parallel efficiency. Now, sometimes you're going to have to go a little bit further out on the curve. So, for example, if a job would take an unreasonably long time at lower core counts, or if a shorter time to solution helps you make progress in your research. So I'm going to say, if nobody wants to wait a week for their job to complete, and having that week-long delay every time, it's going to hamper the rate at which you can get your research done. So yeah, in those cases, you might want to go a little bit further out on the scaling curve. If your code does not have checkpoint restart capabilities, that means that you can stop the code, write out the state of the code, read it in later and restart. Then you need to make sure that your runtime is short enough that you don't exceed the queue limits. And I guess I shouldn't have said one week earlier. Our standard queue limit is 48 hours on Expanse. So in that case, if running at smaller core counts didn't let your job finish in time, then you'll need to potentially run at lower parallel efficiency. Now, sometimes it's really critical that you get a solution at a certain time. So if you're doing work where you're collecting new data every day and it has to be processed overnight and available for analysis in the morning, yeah, then you might need to run on more cores, even though your efficiency is lower. And if you're doing something absolutely critical, and you probably wouldn't use our supercomputers for this, you might use dedicated resources, say at the National Weather Service or the Hurricane Service, or you're doing tornado or tsunami prediction, where even getting the answer a little bit faster is really valuable. Yeah, then you can be running way out here at low parallel efficiencies. Just make sure, though, that you're not running on so many cores that the time versus core count curve actually turns up and starts taking longer to run. And that is something that will happen. And then one other consideration I'll just touch on it briefly here, is if your code has a large memory footprint. So when you're using these allocated resources like Expanse and Bridges 2, you can normally request memory in proportion to the core count. So on Expanse, we have 256 gigabytes of memory and 128 cores on a standard compute node. By default, you get 1 gigabyte, but you can request without extra charge up to 2 gigabytes. But if you need more memory, if you need more than 2 gigabytes per core, you're going to need to request more memory or more cores to get that memory. So in that case, it's okay to run it per scaling, but also consider using specialized large memory nodes. And we have a few of those on Expanse, and there's a whole bunch of them at resource at PSC. So just about done here. We really only scratched the surface. So Exceed and SDSC have many training resources covering a wide range of topics. So I suggest you look at the Exceed training page and the SDSC College to Career training page. And then there are user guides for the nationally allocated resources that contain all of the practical information that you need on job submission and accounting, compilation, data movement, software. A lot of these things are site specific. Not everybody has the same software. The hardware differs, our queue structures vary. So be sure to look at the user guides. And with that, this is my last slide. Just a few things to wrap up. Parallel computing is for everyone who wants to accomplish more research and solve more challenging problems. You don't need to be a programmer to use parallel computers, but you do need to know some of the fundamentals so that you effectively use the computers. A few of the technical points: think of a process as an instance of a program. Threads run within a process and access shared data. Openmp are the most common ways used to parallelize codes. We talked about scalability. Keep in mind that Amdahl's law is an upper limit in scalability, but there are a lot of other factors that affect it. And then finally, know how to display your scaling data and choose your core counts. And as I mentioned earlier, the code you use to generate some of these figures in this presentation are available on this GitHub repo. I will paste this into the chat. And in fact, when you're creating scaling curves, feel free to use my Jupyter notebook. Just paste your own data in there, and it will take care of everything for you, including the lines showing perfect linear scaling and the right-hand axis with parallel efficiency. And with that, I am happy to take any questions.
Feel free to unmute yourself. I actually just enabled that, so you can do that right now.
Yeah.
For anyone who has questions.
I have a question. You mentioned weak scaling. I'm still a bit confused with regards to strong scaling. I always have trouble distinguishing the two. How would strong scaling differ from weak scaling? How could I tell them apart?
Yeah, so I should have gone into a little more detail on that, and I will the next time I do this talk. So strong scaling is typically what most of us think of as scaling. We have a fixed size problem, and we're going to run it on more and more cores and look at how the runtime varies. So let's say it's molecular dynamics problem. It's we're simulating 10 million atoms, and we're simulating that same problem on 1 core and 2 core and 4 core and 8 core, so on. So weak scaling is when we allow the problem size to grow with the amount of hardware that we're using. So going back to the molecular dynamics example, we might be running molecular dynamics with 1 million particles using 1 core, and then 2 million particles on 2 cores, and so on and so on. So if the problem size grew by a factor of 100, we're going to use 100 times more hardware. And then for ideal weak scaling, we'll see that the runtime stays constant as we keep the amount of work per process constant. So Maria, did that answer your question?
Yes, thank you. That makes it much easier. Thanks.
Good. Thank you. Any other questions or comments?
Hi, thank you again for the presentation. That was really helpful. I had a question about threading and threads and processes that might be kind of tangential to this, but just trying to wrap my head around it. So when, in Python or R, and I know it calls functions in C or Fortran, like when you're doing that. So are those processes that it's calling, are those run within the thread, the main thread of R or Python, or is it somehow external to it?
Ooh, well, one thing that gets sometimes it's external. So if you're, for example, using NumPy within Python, you're accessing linear algebra libraries that have been most likely written in C++ or Fortran, and they'll just have Python wrappers around them. And that parallelization, that could be implemented either as threads or processes. And I know in Python, there's something a little quirky with the way that it handles threads, but I don't know enough to go into more detail. But yeah, so sometimes it could be within Python, sometimes it could be external, and it depends on how it was implemented in that external library. So like getting back to the NumPy example, I believe by default for the linear algebra, for linear algebra routines, by default, you're actually getting Intel's MKO library. And again, when it comes to parallelization, it's however MKO implemented it. Did that answer your question? Okay.
Yeah, that was helpful. Thanks.
All right, and then we got a question, another one typed in from Anmol Kapoor. Regarding the myth about adding additional hardware, would it ever get to the point where adding more hardware makes the program run slower? Yeah, yes, absolutely, absolutely. And I think I mentioned that. As let's say I have a straight MPI application, and as I use more and more processors, the amount of work per process is going down. So let me just share my screen again. Let's go back to this example. Where I took my 16 by 16 grid and I divided it up into 4 chunks. So now imagine that I had divided this into 8 chunks. So now we're going to have really, really small pieces on each process. We're not doing very much work, but we still need to communicate a lot of data. And of course, we could get all the way down to the point where we divided this across 256 processes. And now each process just has one cell, but it still needs to have that whole halo of ghost cells. So that is undoubtedly going to run considerably slower than if we had used a smaller number of cores. So yeah. And question from Daniel: is each core limited to one thread? No, you can run multiple threads on one core. I don't know what the upper limit is now, but keep in mind though that those threads are going to be sharing hardware resources. So so that core is going to essentially have to flip back and forth between executing instructions for one thread versus the other. Now there are some times though when running more than one thread per core does make sense. This I think applies more in business applications where we have very irregular patterns of data access. And while one thread is waiting for data, the other could be executing. But yes, so you can. But for HPC applications, you're generally going to be doing one core per thread. And then we have a question here from Will Castillo at Oak Ridge. do we see different scalability performance between compilers? You know, when it comes to, so for the thread level parallelization, let's say you're using Openmp, that's implemented in the compiler. I haven't seen any difference in scalability, but different compilers though will do better or worse jobs of optimizing your code. So you may that may reflect in the scalability, because of course the more work that you have between synchronization events, the better scalability you may get. Great. Any more questions? Right, I'm going to go ahead and stop sharing. And I know it is, depending where you are in the country, it is at least 3:15 on a yes, and thanks, Marty, for following up on the MPI implementations. So it is at least 3:15 in the afternoon if you're in the West Coast, and later, much later if you're on the East Coast. But if you're interested, I could give a brief overview of Expanse. But let's do this. I've been talking for a long time. You've been sitting for a long time. So why don't we take a 4-minute break? We'll come back at 3:20 and we'll wrap up with a brief overview of Expanse for those of you who want to stick around. Okay, welcome back, everybody. So I'm just going to give you a very quick overview of Expanse. This is the supercomputer that we have here at SDSC, and that you're going to be using for the rest of the HPC training. So this is our kind of our glossy overview of Expanse. But it's worth pointing out that we have a certain philosophy of the way that we operate Expanse. We describe this as computing without boundaries. We also mentioned the long tail of science. So it is really a supercomputer meant for many different types of applications. Some machines are really meant for highly scalable apps. Others are meant for serving a wide range of users, and we're more on that end. Kind of a unique way of building this, and I'll explain what all of these mean. But this system is built from 13 scalable compute units. So each of these units, you could think of as a rack in the data center, contains both CPU nodes and GPU nodes. And this makes it easy for us to continue to scale Expanse. So if we obtain more money like we did for our industrial user program, we're able to add a couple more racks of identical hardware. It's what we call a data-centric architecture. It's really meant for working with lots of data. We have fast I/O, we have SSDs directly on the nodes. We have 12 petabytes of performance storage. This is Lustre. And we're going to be bringing on a 7 terabyte Ceph object storage. Mentioned the long tail of science. Just mention a few of the applications here, but it's really just about everything from astrophysics to social sciences. And then we have a few innovative features. I won't really be going into these, but we can enable something called Composable Systems, where we integrate hardware both on Expanse and other resources. We really support high throughput computing, science gateways. You think of these as web interfaces that allow users to run jobs on the supercomputers, interactive computing, containerization, and in some cases, particularly in support of the science gateways, we allow bursting to the cloud so that jobs could be submitted to Expanse, but kind of under the hood will actually be executed on cloud resources. And I just want to mention all of the people who work on Expanse. You probably don't know most of these folks. I, of course, know all of them. An incredibly hardworking team. Main takeaway from this is it is a lot of work standing up and operating a supercomputer. Everything from the from the sysadmins, the people who do the cabling, the data center operators, the user support, which just works so hard, the applications experts, the human resources, and the accounting and the grant management. It really does take a small army to operate one of these things. So, a summary of the Expanse system. I mentioned these scalable units. So the whole system contains 728 compute nodes. Each of the standard nodes has 128 cores. So we're at nearly 100,000 compute cores. If you add up all of the DRAM, all of the main memory, it's an amazing 182 terabytes of memory. And then we have those SSD devices on each compute node. So that gives us close to a petabyte of this NVMe, non-volatile memory storage. We also have 52 GPU nodes. Each of those nodes has 4 GPUs, so a total of 208 GPUs. A lot of GPU memory. Again, those GPU nodes also have local NVMe. And then we also have a small number, 4 of these large memory nodes, each with 2 terabytes of memory. And I mentioned this earlier, the 12 petabytes of Lustre parallel file system, another 7 petabytes of Ceph, and 1 petabyte of home file storage. So this is what one of the racks looks like, the SDSC scalable compute unit. So it has 56 compute nodes in it, 4 GPU nodes for a total of 16 GPUs. And this is all networked using an HDR InfiniBand network. And everything is direct liquid cooled. So this makes the system a little more energy efficient. And I believe that it also makes it a little more reliable. When back in the days when everything was air cooled, data centers, if they would look at a analysis of where hardware failed, it was often hardware at the top of the racks that failed a little bit more often than hardware at the bottom, because you have cold air running under the floor, comes up through the perforated tiles. So you get a lot of cooling near the bottom of the rack, but not quite as much at the top. And the direct liquid cooling helps address that. So these compute nodes, powerful nodes, that they're built using 2 AMD EPYC Rome processors, and each of those has 64 cores. So for a total of 128 cores per node, and a lot of memory in there, 256 gigabytes of DRAM. And then we have the non-volatile memory and the SSDs. GPU nodes, each of these, what did I say it was 52 GPU nodes. Each of those has 4 NVIDIA V100s. So I know by now there's another generation of the NVIDIA hardware. It's hard to keep up, but these are really, really powerful GPUs. And I believe that it gave us close to twice the performance in some applications relative to the previous generation, the P100. And then we have a few of these large memory nodes. Look a lot like the standard CPU nodes, except loaded up with a lot more memory. They're the same processors, those 64 core AMD CPUs, and 2 terabytes of memory. And then I won't get into the details here, but basically we have the system tuned for HPC workloads. Those of you who are a little bit more into hardware and into the BIOS settings, there are different ways that we can configure the CPUs, but we pretty much have it tuned so that it will give the best performance for an HPC workload. Just to show you a picture of what this direct liquid cooling looks like. So there's a lot of plumbing in the data center. Eventually, when we're done with this pandemic and we can start doing things in person, everybody who's local is welcome to get in touch with me, and we can do a tour of the data center, hopefully this year. The topology, And this is where a lot of money goes into a supercomputer. It's in this networking. So especially for applications where it's really critical that we can rapidly transfer data between the nodes, we need to have this high performance network. So we're using something called InfiniBand. You could think of it as being equivalent to, say, a high-speed Ethernet, except it gives you an even better, even lower or better latency. Let me see, we have a comment in the chat. Oh, okay. And moving on, for those of you who are interested in network diagrams, the point of this is basically to show that Expanse has fantastic connectivity to the outside world. So we have access to Internet 2, Open Science Grid, the scenic networks. We have an integration with Amazon Web Services for the cloud bursting for some applications. So even though we have really good high performance storage here, you've got really powerful connectivity to the outside world. And that's going to be important if you're pulling in data from microscopes, sequencers, sensors, whatever your data source is that's outside of SDSC. We have tiered storage. We have this local NVMe scratch drives that are available for the duration of your job. So sometimes you might want to stage data sets there. You might want to store your temporary, your scratch files there. I mentioned the Lustre parallel file system. This is the workhorse for the supercomputer. We are going to be deploying soon a Ceph object-based storage. And then we have a high availability network file system for your home directories. And just want to mention that this idea of having SSDs, solid state drives in every compute node, this has a long history. It actually goes back to supercomputers to Gordon, where I believe we were the first large-scale deployment of SSDs in supercomputers, and now it's pretty much become the standard. This is more for the sysadmins. If you're interested in how we manage the cluster, we're using something called the Bright Cluster Manager. The operating system is CentOS. The scheduler, which you're going to be learning about a lot more, is Slurm. We have a Kubernetes partition on the system for these composable systems I mentioned earlier. And then finally, one of the things that's unique about Expanse is how we operate and allocate the system. So you can request full nodes, but you can also request portions of a node, because we recognize that there are a lot of applications that may only scale to a few cores, 2, 4, 8, 16, 32, and it would be a waste to use the entire node. There are some systems like Stampede 2 at the Texas Advanced Computing System, which do not allow shared nodes, but we allow it here. You essentially pay just for the portion of the system that you are using. The last bullet here, we say Expanse has multiple resources that can be tracked. We'll be getting into that in a little more detail in some of the subsequent sessions. Basically, we can do a billing that's based on the cores or the memory that you use. And then finally, and I think this is my very last slide, again, this will be covered in the session on job submission. We have different partitions or queues for different types of jobs. So we have a compute queue if you need exclusive access to a compute node. We have a shared queue if you want to use fewer than 128 cores. We have a GPU queue, which will give you exclusive access to all 4 GPUs on a node. But more commonly, you're only going to need 1 GPU. So we give you an option to submit a job into the GPU shared queue that requests 1, 2, or 3 GPUs. We have a queue for accessing the large memory nodes. And then we also have debug queues that give you priority access with very short wall times. And these are excellent for doing testing and development. And then finally, we have a preempt queue and a GPU preempt queue, where you can run your jobs at a discount on free nodes, but they could be preempted by jobs submitted to any other queue. So with that, I am going to, let's see, yep, that is my final slide, and I will wrap up. So is there any questions about Expanse?
I do have a question regarding the compute nodes and GPU nodes having all of them SSDs. So are those independent from the PFS? Are they used as staging storage or like burst buffers? And the second question, any disadvantage to having so many SSDs in terms of energy consumption?
Okay, so let me answer the second one first. But really no disadvantage of having the SSDs due to energy consumption. So first of all, you generally do want to have some node local storage, and SSDs are incredibly energy efficient relative to hard drives. So yeah, we're really not taking taking an energy hit there. In fact, when the SSDs are idle, they draw a truly negligible amount of energy. So yeah, so it's actually the energy efficient solution. And then, and can you repeat the first part of the question, or just remind me?
Yes, on the usage of what's the use case that benefits from them, and how does interplay with the Lustre PFS?
Yeah. So the so the use cases. So first of all, the SSD is only available to your job while it's running. So I think maybe I didn't quite speak correctly when I said staging data. But so you have it available while the job is running. The typical use case would be if you need to write out temporary files. So this is really common in computational chemistry, where they need to save an integral file. So instead of writing that out to Lustre, or even worse, to the home directory, you can write that to the SSD. Another use case that I found was really helpful. Years ago, I was working on an application in computational finance, where we would be analyzing, in entire markets like the New York Stock Exchange and the NASDAQ and the BATS. And we would end up generating thousands and thousands of mostly small files. And rather than writing them out to the hard disk, I wrote them directly to the SSD. And then from there, either created a tar file and then saved that, or I could write from the SSDs directly into a tar file then on the Lustre parallel file system. And that way, on Lustre, we're only dealing with a single large file, rather than these thousands or tens of thousands of small files. So yeah, a lot of times if you want a way to collect all those small files, or if you need that temporary space. So you don't really get a lot of benefit from, say, taking your data set, reading it from Lustre into the SSDs and working with it from there, because you still have all that expense of reading from Lustre. But if you said, had to repeatedly go to that data set, but accessing it in a fairly random manner, then the SSDs would be helpful, because they have much faster random access than a hard disk.
Oh, that's great. Thank you.
And question from Anmol Kapoor again. When it comes to maintenance of Expanse supercomputers, what parts get replaced over time? CPUs, GPUs, SSDs? Now, so I'll attempt to answer that, and if my SDSC colleagues want to chime in and expand on it. So I would say what seems to die most often is, I already wrote all of them. So Marty, correct me if I'm wrong, but I recall that it tends to be the really low-tech kind of stuff like power supplies and previously when things were air-cooled fans, that would fail a lot. And Marty, if you want to chime in, I recall that GPU, CPU, and SSD failures are fairly uncommon.
Yeah, I would say so. I would say that you're right with fans and power supplies are probably the most common. Maybe memory DIMMs too.
And also, I guess on Lustre with all those hard disks, we're probably replacing hard drives all the time. But that would be generally transparent to the users because we have rated file systems so that they can tolerate disk losses. And any other questions? All right, if not, I guess we will wrap things up. Thank you everybody for spending your Friday afternoon with me. Have a great weekend and hope to see you next Friday.